The screen. Okay. Roger that. Sorry.
I still haven't found the one for the 5-path one, but I'm not really sure if there is one.
Right, you think you found one? Okay.
I don't think I haven't found one.
Oh, you haven't found one? Right. Yeah, I haven't. I thought a little bit more about that, but I didn't find one either. It seems to extend a bit, but then break down after some number of steps. Is that what you found?
Yeah. It's like one of them has 3 degrees. Or something like that, I think. Speak up.
Yeah. That might be a good one to test on the with the computer, see if that comes up with something. I suspect that if we're having to go to several steps in order to find a problem, then it will take too long on the computer or the laptop anyway. We might have to put it on a more something more powerful.
I thought we tried it yesterday.
Yeah, but we didn't get an answer, did we?
Nah, but
yeah. Right. Well, I think perhaps we can keep thinking about that one, see if we can come up with something. And I'll check with some of the others who've been thinking about this, and yeah, I'll write to them shortly and see if they have any other thoughts or have made any progress. Okay, did you read about or have you thought more about the polygons or the end cycles? If we start with a polygon and then try add a center and then try to extend that, have you thought about those cases?
Yes, like the triangle, square, pentagon. It's like I looked it up. It's like a platonic solid or something.
Platonic solids, yeah.
And then you said the hexagon tessellates nicely and the rest don't. We looked up like the hyperbolic and elliptical tessellations and the drawings or something.
Yeah.
Yeah. We looked at some of that. I saw that the pentagon could be tessellated in elliptical geometry as well, I think.
Right. So the pentagon, we add a center, and that gives us what 5 triangles inside the pentagon. And then, so what do you get when you try to extend that? Did you see?
Yeah, it's like the 20 face.
Yeah, that's right. One of the platonic solids.
The largest platonic.
Icosahedron.
Yeah.
That's right. So we get the tetrahedron, the octahedron, and the icosahedron. It's in the first 3 cases, then a tessellation of the plane with triangles, and then tessellations of hyperbolic planes with triangles for n greater than 6. Right. Sorry, our phone's ringing. It'll ring out in a minute. So I'm just wondering now what other examples to think about. We could start trying to make exhaustive lists for the graphs of different sizes. So you saw yesterday on the website, there was a list of the graphs of different sizes and the number of them. You know, up to 4 vertices, we could probably make an exhaustive, give an exhaustive list of the possibilities. Once we get to 5 vertices, well, okay, we already know one with 5 vertices, but we don't know the answer. So we know that at 5 vertices is where we're starting to get a problem. So why don't we, for the rest of the time, try to start making this list and getting some report on what could be said about the small graphs anyway.
So ordering them by number of vertices.
Yeah. So you see, if there's 2 vertices, then there's only 2 graphs. There's either the 2 points, or there's just the 2 vertices and edge. And we know the answer in both cases. If it's just 2 points, then the graphs extend to a polygon or to the line. And if it's an edge, then when we add a center, we get a triangle, and then that's already complete. There's nowhere to go. So there's a complete answer there. Now with 3 vertices, there's not many graphs, and we can check all the answers there.
Yeah.
So what have you got to what could you use to write a report in? Have you got, what software might you use?
Oh yeah, we have.
Yeah.
We can write it up in latex or something like this.
LaTeX, yeah, that's good. Yep. Let's start doing that. Writing a LaTeX report on just what the possibilities are for the various graphs up to 4 vertices. I think we can probably do it up to 4 vertices. I think I worked out all those out by hand once, but I didn't write it in tech or anything. It'd be good to have a tech report. So should we try doing that? If you're familiar with tech, I could send you the tech for my slides of my talk last night as well, if you're interested.
Oh yeah,
Yeah, I think it went fairly well. It was on an hour later than I thought, and so yeah, it finished quite late, which is why I'm a bit slow this morning and why I'm working from home. But yeah, I think the talk went fairly well. I can send you the Beamer slides for that, and you could perhaps play around with those as well and just see if you prefer a different color scheme, for example. Now, all right. So I'll write to some of the other people. So one of them will be Marcus, who we talked to yesterday. But there's another student, a teacher, whom I'm meeting with at 12 anyway. And then there's someone else. Okay, so did you look at the web page, the 0-dimensional?
Yeah, I looked at the tree drawing thing.
Yeah. I was going to say, if you look at the home page there, you'll see one of the people is Stefan Tournier. He's also been working with Marcus and Aditya on this, so I'll write to him as well. But you looked at the tree drawing. Did you play around with those?
Yeah,
tools?
I tried it. Yeah, but I think. like I tried it the first day you sent me, but I think it was either I think either like I didn't know how to input the points or something. I think. I'm not sure.
Ah, okay. So which one are you looking at? So the models for drawing trees?
Yeah, like the first one, I'm pretty sure.
Okay, let me just go to that. Okay. So if you, perhaps I'll sign in from the laptop as well.
George Willis had the way.
Yeah, so I'm signing in from my laptop so that I can share the screen from the web page. Okay.
Oh yeah, so I tried using like the Vertus one, and
Yeah, I'm trying to share the screen, but it says I can't.
yeah. Hang on.
Screen sharing.
How do you know it's not on?
Because it doesn't have the video.
Okay, thank you.
Yeah, so yeah, I remember using this and I was like just screwing around with the degrees, the valency thing.
Yeah.
But I didn't really know how you would like draw your own like
Okay, draw your own graph.
yeah.
Right. We are starting to have some tools to do that, but they're not on the website yet. So for that one, what I might do is I'll write to our IT person who's doing this and see if he can make some more of the tools that are under development available to you.
Yeah, don't worry about it. I was just wondering. Yeah.
All right. Okay.
I did try around with a little bit. But yeah.
Right. Okay. So you, all right. Perhaps I won't do that then. But yeah, so you can increase the
Yeah.
the valency and number of levels, the edge scaling. Yeah, as you increase the valency, you need to change the edge scaling. Perhaps we should try to get rid of the labels. It's fairly touchy. The slide is fairly touchy. Anyway, that's you can have fun playing around with this. And then you can once you get if you get a picture that you want to use, you can include in a document. And this is something we might want to do in the report on this vertex transitive graph project, we can export the image as a PDF. All right, so you played around with that a little bit. Did you want to have any other questions about it? Sorry.
I didn't look at like if you use the edge or the axis or something.
Yeah. Right. So let me just say what these are about. These are three different ways of looking at a tree. So with the vertex, well, let's just go back to this one now. With the vertex focused one, we put a vertex at the center and then build out from the tree in a regular way. With the edge focused one, we start with a single edge, and then we build out from there in a regular way. So these are two different ways of looking at the same tree. And the reason we're interested in that, we're interested in symmetry of these structures, and these are two different ways of thinking about symmetry. So we can think of symmetry around a vertex, which is the vertex focus model, or we can think of symmetry about an edge or the midpoint of an edge, which is the edge focus model. And then there's the third one, the axis focus. Well, that's not coming out too well. Let's see if I can change this one a little bit, increasing the levels. That's starting to, you can see this is not exactly how we want it to look. Perhaps I'll go to the other approach. In doing this, you have to think about algorithms, about how you want to instruct the program to distribute the vertices. This one's not a particularly good solution. But anyway, what I wanted to say was that we have an axis. So we can think here of that we can translate along this axis. So that's another type of symmetry of the tree. Let's see about this one. Yeah, that's we can't. We don't seem to be able to adjust the width here. Yeah, this one's not very good. So the axis focus models are not very good at the moment, but they correspond to the three types of symmetry of a tree. This was something that was shown in a paper that was published in 1970, that if we have a regular tree, there are exactly three types of symmetry. There's the vertex focused, the edge focused, and the axis focused. And that's one of the things we want to do in our overall project is understand symmetries of graphs, and that will involve finding nice ways to draw them. So you saw that in the examples that Marcus was showing yesterday, we came up with some graphs, and then we wanted to draw them. And it was sometimes hard to see what the shape was, and what the symmetries were. And so that's going to be one of the aims of our project to well, that is one of the aims of our project, to find ways of identifying the symmetries and drawing the graphs so that they show the symmetries. And the tree is the most basic case. The regular tree is the most basic case, and that's what we're doing here. But there are going to be more more complicated ones. I guess another one is the where it's easy. It's for the regular polyhedra or platonic solids. It's easy to see the symmetries, and the same for the tessellation of the plane. We can draw them in a way that we see how they are symmetric. But in general, that's going to be a problem. We might have something that is symmetric, but we want to be able to draw it or think about it in a way that shows the symmetry. And that's what we're heading towards with these models for drawing things. We want to use these to produce pictures to include in publications and talks, but we're really interested in the theory behind it of how do we draw things to show the symmetry. Yeah.
So yesterday you already had a program for converting like adjacency matrices to a visual representation, right?
Yeah. There are many. Yeah.
How does it work?
Well, that's just something that was already created by somebody else. There are actually a number of programs that people have created for drawing graphs. I think ultimately we want something a bit more specialist that works for highly symmetric graphs. But but there already exists software for drawing graphs, and there's a number of ways in which they work. So Marcus was using a particular one yesterday, but in fact there is somewhere between 5 and 10 different algorithms that can be used in that sort of package that he was using. There are other methods that are used for trying to draw graphs. One that we have been using is that you imagine them as a physical system, and you imagine the edges as springs pushing the vertices apart. And so the idea then is that you want the vertices to be separated out as much as they can be, so that you get the sort of the best view, rather than so things are not too crowded. And this physical model is used where we imagine the edges as springs pushing the vertices apart, and then a calculation is done of all the physics of what it would look like with this force pushing the vertices apart. So that's one approach that's used, and I don't know if we have it. Yeah, it's not on the website at the moment, but there was we do have something that where you can add a vertex, and then the whole thing will readjust itself to according to that algorithm.
Yeah.
To change shape. So yes, there are various algorithms. There's and there's a theory. There's someone by the name of Mike Fellows who's written about how to draw graphs, so that you can see them, see the information as clearly as you can. Now, there isn't always a good solution. Some graphs are just too complicated to do that, and then we want to go beyond graphs as well. We might want to fill in. So if we look at this particular one here, we see the little triangles. We might want to fill those in and have a face as well, or just with a polyhedron. We might want to fill in the between the edges and add triangular faces or pentagonal faces or whatever. We can try to do that, but then we might get something that can't actually exist in 3 dimensions. and it's very hard to visualize that. There's another project, and I'll send you a link to that as well, that we are getting going, of trying to visualize some of these shapes that can't be drawn in 3 dimensions. There are certain objects called buildings that are not the usual sort of buildings. They're a mathematical idea that are related to graphs, but they have, as well as having vertices and edges, they have faces. So 2-dimensional faces, or even higher dimensional faces, and they are all glued together according to some rules, much like the way we glue trees together with vertices and edges. So these regular trees are a special sort of 1-dimensional case of buildings, but there are higher dimensional things, and the problem with those is that typically we can't visualize them in 3 dimensions.
Yeah, that makes sense, because it's a bit hard to.
Yeah, they just don't work. They just don't go into 3 dimensions. So for example, the next level up, we can think of a tree as containing a lot of lines. So if we just we can follow a line through here. You can see where I'm tracing the arrow. We just follow a line through there, and then there are infinitely many lines through here. And one way to think of the tree is as all of these lines glued together according to certain rules. Now, in the building, we replace these lines by higher dimensional things. And actually, one of the things that they can be replaced with is the tessellation of a plane by triangles. So instead of having a line, as we have here, we would have a tessellation of a plane by triangles, and then we glue those together in according to some rules, infinitely many of those. And that gives us what's known as a building. And they are important for some of the things we're doing. They come up naturally. They are naturally occurring objects. Perhaps I won't say anything more than that, that we are interested in, and people study them quite a lot. But we can think about them geometrically in some ways, but we can't visualize them in 3 dimensions. So this whole problem of how do we visualize a graph is a big one, and it doesn't have a good solution in general. It doesn't have a good general solution, but in particular cases, such as the one we're interested in, where they're highly symmetric, then where there are certain things that come out of the theory that tell us we should be focusing on, and we see that in the 3 different focuses for the trees: the vertex, the edge, and the axis focus models. But then we'll want to have similar things for other highly symmetric graphs. So that's a little bit of the picture of what we're involved in the larger project. But the particular thing we're talking about just now is, well, are there other highly symmetric graphs that we haven't thought of yet? So the buildings I mentioned, they are a very important class of graphs and or structures, and there's a lot of work done with those, but we still don't know if we have all of the possible highly symmetric graphs.
What do you mean by highly symmetric?
What do I mean by highly symmetric? I mean vertex transitive.
Okay.
Yeah. So they look the same from every vertex. Okay. So let me just make a note. I'm going to send you some things, aren't I? I'm going to send you the slides. But I'm also going to check with others about the line with 5 vertices. Was there something else I was going to send you? What about a LaTeX document? So should we start preparing a LaTeX?
Yeah, up to 4 vertices. Yeah.
What's that?
A report on the vertex transitive graphs up to 4 vertices.
Yeah. Are you happy to just start that document, or do you want me to?
Yeah, we can start it ourselves.
Right. Okay. Great. All right then. Oh yeah, I might see if I can find some other links to send you about graph drawing and building.
Yeah, that'd be really nice.
Yeah, that would be great. Well, I'll go get my laptop.
Oh.
All right. So I'll do that, and yeah. So keep thinking about the 5 vertices in a line, and perhaps get the report started. Okay. Shall we meet again later today?
Yeah. When would you like to meet?
I have quite a few meetings today. I might have one at 2. Shall we meet at 3?
Okay.
Yeah, okay.
That's fine.
All right. Well, I'll see you there. And yeah, in the meantime, send you some of these things.
Yeah, that'd be really great.
Okay. Well, I'll stop the screen sharing and leave that one. Right. Well, I'll see you then at 3.
See you.
Okay. Bye.
Bye.
Wait, share with me.